Welcome. In that video, we are going to talk about neural radiance field, and we are going to review the iNeRF paper, which consists in inverting NeRF for doing pose estimation. So basically, when we want to estimate camera poses, so let's say we have the picture of an image. Usually, what we need is the 3D model of the object. Well, there are different approaches, but one approach is to we have the 3D model of the object. And therefore, we try to find the camera position such that when we project the 3D model to an image, we get an image that is similar to the image we've seen. So basically, here this is a bit what they are doing. Here they do not need a 3D model of the object, which is a great asset, but they need a 3D. Well, they need a NeRF model of the object. So for example, here let's assume that we have this object. We have a 3D with a 3D model of it. A 3D NeRF model that we've trained, and then we want to get the position of that. So basically what we're going to do, we take a camera matrix and we render the NeRF model with that camera matrix. At the beginning we just initialize the camera randomly, and this is what we get. So we are overlaying the rendering with the image. So on one side we have the real image that we've captured. On the other side, we have the rendered NeRF model with the current approximation of the camera matrix, but that has been randomly initialized, and therefore they do not agree. And then we take the MSE loss between them, or any other loss, and therefore little by little we update the camera parameters until the projection of the 3D model matches the image we've captured. So basically it's an inversion problem where we are solving like ax minus b, and usually we take the L2 norm of that, so the L2 loss between ax minus b. Usually when we train a NeRF we optimize for x. I'm sorry, maybe that's a bit small, I'm not sure if you see that. But basically, usually we optimize for x. So x is our 3D model and we optimize x. Here, basically what we're doing, we're optimizing the A operator, so the 3D projection operator. So A englobes the camera matrix or the camera model, and we optimize the camera model such that our projection of the 3D model works fine. Okay, so yeah, sometimes it's a bit like the snake that eats his tail. Because we need a 3D model of the object. But yeah, in a lot of real world application, let's say that you need to calibrate your optical system, you have access to your 3D object, to the object you are calibrating. Usually you don't have the 3D model of that. That's very unfortunate, but you can easily take pictures of it and reconstruct it in 3D. Okay. So here we have an example of the approach. Basically, usually we have the exact same procedure for training NeRF. So we shoot rays in the scene. For the sampled pixels or for the selected pixels, we render the color, and then we render them using the volumetric rendering approach. Then we take the loss between the observed pixels and the rendered, and then we backpropagate. Usually with NeRF, we will backpropagate to the NeRF model to optimize the NeRF model. But here, this is not what we want to optimize. We want to optimize the pose, the camera model. If you are unfamiliar with NeRF or that the volumetric integral is not clear to you, I have a lot of other videos about that on my channel. And I also have a full course about that on Udemy. I will put the link in the descriptions if you're interested. They also mention different strategies to sampling the rays. So for example, with NeRF, usually during training, the pixels are randomly sampled. Here they suggest different strategies to do that. Random sampling, interest point, interest region. We won't go to that into details. I invite you to have read at it. But basically we can see here that by being smart in how you sample your pixels, for example using interest region sampling, you get first you get better results, or maybe at least you converge faster. We can see that after 200 time steps, I believe that's 200 gradient step, the results for the interest region sampling are much better, and we can see that we converge much faster. What they also suggest in the paper, which is very interesting, is that they could also use the approach for improving NeRF by augmenting training data. So let's say that you have images in your dataset where the camera pose are unknown. You can use that method to get the camera pose and then add those data to the training set. So maybe it can be taught about semi-supervised learning. Maybe that's not the best way to see it, but with semi-supervised learning, you have some labeled data, some unlabeled data, and you are combining supervised with unsupervised learning to get so that you can leverage the unlabeled data and get best results. So here maybe we can think it's not really that, but we can think a bit of that method. It's semi-supervised learning, where we are leveraging the images for which we don't know the pose. For example, let's say that call map failed to approximate the pose of those images. We could use that to approximate the pose and then to refine the NeRF model. Okay, on here it's very interesting. They show an example on the first. Okay, maybe before moving to that, very quickly we can discuss the ShapeNet experiment. So for example, here it's not really a bottleneck, but the issue with that method is that you need a 3D model, a NeRF model of your object. On here you can combine that with PixelNeRF. So I made a video about PixelNeRF. I don't know where they mentioned PixelNeRF. Okay, so basically, yeah, for example, when you use PixelNeRF, you don't need to do any 3D reconstruction. Well, you don't need to do any reconstruction at inference time. You just receive images, and then PixelNeRF can directly reconstruct or generate novel views from the input image. It doesn't need to do a reconstruction at inference time as opposed to NeRF. So basically, that means that if you pre-train a PixelNeRF model on, let's say, for example, ShapeNet, that is, for example, on the ShapeNet dataset, you have images of cars. Then that means that you can directly use that model at inference time without needing a 3D model or 3D NeRF model for each object. On here, they show some results on that real-world scenario where they take pictures of that image, well, pictures of that car of that toy, and they can infer its pose. So that's very, very interesting, where they can track in real world the pose of the car without training the model on that car specifically. They just pre-train it on synthetic data, on ShapeNet data, the PixelNeRF model, and then use it in combination with that method to estimate and to track the pose. So that's very, very interesting. Okay, that's it for that paper. I really hope it was helpful to you. If you're interested in NeRF or machine learning in general, subscribe to that channel. And if that video was helpful, please leave a thumbs up. It's really helpful to me. Thank you.